Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's show is imaging an eclipse. And here to tell us how to do that is Tim Campbell. Tim, welcome back to the show.
Thank you for having me. Glad to be here.
Good, good. Always good to have you on. So we've got an eclipse coming up in April. So let's start with some safety.
Okay, April 8th. One of the things that I get asked about a lot is how do you look at an eclipse? During totality, when the moon is completely obscuring the sun, you do not need to worry about eye safety. You can look directly at the eclipse and see the solar corona, but that's only when the moon is completely covering the sun. At all other times, you need some of these. So these are eclipse viewers. These are cheap. They cost, I don't know, a couple dollars. I tell people, buy 25, give them to your friends and family.
Sure.
But you want to make sure that you have these on. These block out 99.999% of all the light. That's one photon out of every 100,000 makes it through this filter. If I put these on here, I see absolutely nothing. Even the bright studio lights, nothing shows up because of how well they block. That's for us. I have had people say, I've looked at the sun before, I'm okay. It's a delayed thing. You stare at the sun too long. It is in seconds, not minutes. That's too long. And it's like getting a sunburn. You don't instantly get eye damage. It takes hours, sometimes a day. It could be 2 days. And then you need to go see an eye doctor, and maybe they help you and maybe they can't, depending on the damage. So for a buck or two, don't gamble your eyes.
Absolutely.
For the camera, you can get something like this. Now, I have a camera that has a thread-in filter on the front of the lens. This one is made to cap on the front of a telescope. So imagine a telescope, you just cap it on. It's the same filter that's in there.
Okay.
And that keeps the camera from being damaged. Again, during totality, you take this off. But every other time, you leave it on.
Exactly. So our next question is about netting it out.
Yeah, so the netting it out is all about the complexity of doing eclipse photography. So there's a well-known guy, Ford Amateur. He's a retired NASA physicist. He's the guy who does all the eclipse predictions, and he's also known as Mr. Eclipse. His website is EclipseWise. When he gives talks, he talks you out of it. He says, don't do this, but let me explain why he says don't do this. Totality only lasts a few minutes. If you've never seen a total eclipse before, you want to look up and appreciate what's going on with your eyes. You don't want to miss it. If your head is in your camera gear and you're trying to manually control these exposures and take all this, you're going to miss it. And those exposures are complicated enough that you're probably going to blow a lot of those exposures. So what I do, and what he taught me to do, is to use software that completely automates the capture. A computer drives the camera. It's changing the exposure all the way through the eclipse. It's on autopilot. I start that process rolling. Everything has been pre-programmed. I enjoy the eclipse. The computer does the work.
Perfect. As long as everything works out the way you plan.
As long as everything works.
Yeah.
And you do a lot of pre-testing to make
There
sure
you
it
go.
really is going to work.
I mean, Tim, it's computers. What could possibly go
What could
wrong?
possibly?
That's for sure. So you're talking about computers. What are the essential gear?
Okay, so the essential gear that you need is a camera with the correct focal length. So we've got a table of focal lengths that you can look at. What you want, so depending on the camera that you have, recommended would be a DSLR camera. Your phone camera is not really going to be the right equipment for this. But with a DSLR camera, they come in 2 different sensor sizes. Commonly, there are others, but it's mostly 2. It's not the sensor size so much, but it's how big is the sun. So the sun is 400 times bigger than the moon. It's also 400 times farther away. In the sky, that causes them both to appear to be about a half a degree from edge to edge. So if you look at the sensor, you've got the long way and the short way. In the short dimension, you want the sun to occupy at least 1/4 of that distance. So in other words, at least 2 degrees. Optimal is about 1/3, so 3 suns top to bottom. No more than 2 suns top to bottom, so no more than 1 degree. That will give you some sun in the middle, with enough spare room on the side that when totality happens and the solar corona is shining out, you'll actually be able to see the corona. If you go too tight, you'll miss the corona in your photography. You won't get that. You could go a little shorter if you say, well, I don't have a lens that will even get me to 1/4. I can only get to 1/6. Fine, you're fine. Do 1/6 if you have to. The other equipment that you're going to need is, of course, to drive this automatically. Remember I said every exposure is going to be a different, it's not just clicking at the right time, it's changing the exposure and clicking. So the software that's controlling the camera is going to be driven on a computer. Maybe you have a good camera that will let you actually sequence the shots. If every shot is a different exposure and it can handle that, most cameras won't do that. Or an intervalometer that you plug into the side of the camera that triggers the shutter won't do that. So you have to be able to control the different exposures. When you do that, of course, now you're going to need a cable between the camera and the computer. And it helps for it to be a long cable. Commonly the cable that came in the bag with your camera probably only a few feet long, probably not long enough. So I have some recommendations. You can get these tethering cables that are like 15 feet long. Perfect. Those are perfect for the job. You're also going to need some memory cards to store that's appropriate for your camera. You're going to need batteries that are good. Make sure that you've got good battery power to last through. I say check the battery about 15 minutes before totality to make sure the battery's not about to die. That would be a good time to change it if it is, because you don't want to be doing that during totality. And then you kind of want to have this thing called a tracking mount.
Okay, tell our viewers about that.
Okay, so I brought a tracking mount here to the studio, and the idea behind a tracking mount is that the Earth is, of course, spinning on its axis. And so we're spinning from west to east. It takes about a day to go around once, which is the definition of a day, right? So what if you had a camera that was mounted on a gizmo that was where its rotation of axis was pointing in the same direction as Earth's North Pole, and it was spinning at exactly the same speed that the Earth is spinning, except in the opposite direction. So Earth is spinning west to east, we're spinning east to west on the tracking mount. The net effect of that is that whatever the camera is pointing at in the sky will not be sliding across the image. It will stay in one place and the camera will be following it. And that's the idea of a tracking mount. So I have one in the studio to show, but here's one that was 3D printed. A friend of ours, Liam Finn, another NASA Solar System ambassador, 3D printed this. So there's a project at Instructables. We'll put up a link for you to get
great,
the parts
because
to do it.
I'm sure some of our viewers would at least like to take a look at that and see if something like that would work for them.
And it's just a piece of threaded rod. You put the camera mounts up here with the lens, and then you put the maybe a counterweight down here. And this little motor keeps this spinning. And you put a little Arduino on. I don't have the Arduino with me, but you put a little Arduino on. They're $25, and it makes the whole thing track. So it's a very inexpensive way to get a tracking mount that works okay. It can't handle a huge amount of weight, but if you've got a lightweight camera and not a super heavy lens, it would work.
And access or own a 3D printer.
Yes, or have a friend that has one.
Well, there you go. Those are good friends, yes. So you mentioned software.
Yes. So there are a couple of big ticket items. One is for Windows users, there's a piece of software called Eclipse Orchestrator. There is a free trial version, but they don't turn on all the features. And you have to license it if you want all the features turned on, and I recommend that you do get all the features turned on. That is perfect because it's completely designed for eclipses. You get a little USB GPS that you plug into your laptop so that the laptop knows the time, date, location, even the altitude matters to time exactly the right time. And there's a script that actually comes with recommended shots. You can modify it if you want, and it makes sure that the camera takes all the right shots at all the right times. If you have a Mac, the same software is called Solar Eclipse Maestro. By the way, these two authors know each other, and they've collaborated. The scripting language that they use is almost identical. The script for one would actually mostly work on another with minor modifications. The trick on Solar Eclipse Maestro is it doesn't work on the latest Mac operating systems. You'd have to run it on a virtual machine. I use VMware. to run an older version of the Mac operating system, and it works fine for me to use the old one. That software is freeware. They appreciate donations, of course, but the other software requires a license to unlock it.
Is there anything else available besides those two?
So you could do, there's something called Set and See that is designed for Eclipse photography. There are other things that are designed generically for astrophotography. There's something called Nina. There's something called Backyard EOS for Canon cameras. There's something called Backyard NIC for Nikon cameras. But those are not specifically designed for eclipses. You can orchestrate what shots it will take and how many seconds or fractions of a second to delay from shot to shot and change the exposure on every shot. But you've got to kick it off. So you're going to have to say, well, I've got a shot, I'm going to start it. It's going to take 15 seconds, it'll take the first shot. 8 seconds later, it'll take the second shot. You've got to try and time that. And some of these shots, you've got a lot of wiggle room on when you take it. You've got almost 4 minutes of totality if you're on the center line. If you're off to the side of the center line, maybe you only have 2 minutes or 1 minute. But other shots really need to be precise. Bailey's beads, diamond rings. If you're off by a second or two, you kind of miss it. So you got to be really careful about that. So it's best to get the software that synchronizes with the GPS.
Sounds good. Now we're going to take a very quick break. If you have a question, please send us an email, and we'll be back with more of this discussion after Term of the Month with Stephen.
Thanks, Don. The term of the month is OSIRIS-APEX. The OSIRIS-REx spacecraft collected a sample of asteroid Bennu and returned to Earth. 20 minutes later, it fired thrusters to meet with asteroid Apophis in April of 2029, shortly after Apophis makes its close approach to Earth. The new mission name is OSIRIS-APEX, with apex meaning Apophis Explorer. Say that 3 times fast. By April 2nd, 2029, the spacecraft will start collecting data on Apophis. Apophis will also be observed from Earth. The 185-meter diameter, 307-meter long Apophis asteroid zips by Earth at 20,000 miles, that's 32,000 kilometers, on April 13th. Shortly after Apophis will appear too close to the Sun to be observed from Earth, so these observations are better done with a spacecraft. The spacecraft continues with Apophis for an 18-month detailed study. Now, Apophis, at the moment, is thought to be a rubble pile. A close approach like this could trigger changes on Apophis. Gravity could disturb the surface with landslides or particle ejections, and OSIRIS-APEX may detect such changes. Mission science goals include measuring material strength, porosity, and density of Apophis. One of the plans is to stir up rocks and dust on the surface with its thrusters. These goals are important because most of the potentially hazardous asteroids are S-type like Apophis, and that's Term of the Month, OSIRIS-APEX. Back to you, Don.
So, Tim, let's talk next about Eclipse basics.
Okay, so I have a simulation that I set up. The site that I chose was Norwalk, Ohio. I picked that particular location because it's relatively close to Michigan. It's on the center line. Because it's on the center line, you will experience totality there for nearly 4 minutes. It's just a few seconds shy of 4 minutes. If you are, let's say, Toledo, Ohio, you are in the path of totality, but you're not on the center line. You're outside it enough that maybe you only get a minute or 2 of totality. So if you want to experience totality, you get as close to the center line as you can. That's why I picked the location. Okay. In this simulation, you're going to see the moon is starting to move in near the sun. There are 4 things that you need to know called the contacts. First, second, third, and fourth contacts. They abbreviate them C1 through C4. The first contact is the moment that the moon first kisses the sun. The edge of the moon has finally touched the sun. That's contact number 1. The moon continues to move across the surface of the sun until it completely blocks all sunlight.
The totality.
Totality starts. That's contact number 2. Approximately 4 minutes later, depending on where you are, it might be a little less, the moon is moved far enough across the sun. Remember that in a total eclipse, the moon is closer to Earth, causing it to seem just a tiny bit bigger than the sun. And so that means that the moon's disk is a little bit bigger than the sun's disk, not by much. It will move to the other side of the sun, and now it's starting to uncover the sun. That moment when the sun starts to uncover, that is the third contact. And then when the moon has completely uncovered the sun, so now the moon and sun's disks are kissing, but we're moving away, that is the fourth contact. The reason these contacts are important is because when we talk about the exposures that you're going to want to take, we'll say, take this shot 9 seconds before the second contact, or take this shot 1.5 seconds before the second contact. And you'll want to know that's what I mean by the contacts, the moment of when mostly it's the second and third contact, when totality is starting and when totality is ending.
Okay.
Okay, I've got a table that I showed just as a refresher. There are a number of shots that we can take, right? So the first is the prominences. So normally to see prominences, those are these hot plasma shooting off the side edges of the sun, requires a special type of hydrogen alpha solar telescope. But during totality, you can actually see it through the camera. And the time to take that shot is 9 seconds before the second contact. And I have the exposures here, and we've got some tables that we'll put up for our viewers, right? So I use ISO 200 and f8 for everything. And then I take that shot at 1/500th of a second. Now, if you know how to do trade-offs, if you say, well, I don't have f8, I'm going to shoot it at f5.6, that's twice the light comes in at f5.6 versus f8, I need to take that shot for half as much time. So instead of 1/500th, I do 1/1000th. But I'm just going to base everything on f8 and ISO 200 to keep it easy. The next shot is the corona, sorry, not the corona shot, the chromosphere shot. So the chromosphere is that it's a higher layer of the sun's atmosphere than the photosphere. The photosphere is the bright white part of the sun that we normally think of when we see the sun in the sky. That's the photo. The chromosphere you can't see normally on a day unless you have a special hydrogen alpha solar telescope to see it, but it is actually a little bit higher. When the sun is being completely blocked, it actually peeks out at the edge of the sun. And your cameras, if there happen to be prominences, we don't know that there will be, but the sun is pretty active, your camera will actually capture those shots. It's about, let's say 3 seconds before the second contact or 3 seconds after third contact. Again, 200 ISO, f8, and 1/5000th of a second. It's a really fast shot to be able to take that. The next shot is called the Bailey's beads effect. So Bailey's beads is because the moon is not as smooth as a cue ball on a pool table. It's got mountains. And so there is a point at which the sun's light is only peeking through gaps in these mountains. And so you get little dots of light around the peripheral of the sun, and they call that the Bailey's beads effect. That effect is 1.5 seconds before totality. That's why I said you really got to be able to time these things right to do that. And you do that at 1/1000th of a second. Okay, the next 3 shots happen during, totality. One of the shots that I want to take is the corona bracketing shot. This is 12 stops of bracketed exposure. So I need to explain what a stop is very briefly. Experienced photographers are used to this term called stops. There are f-stops, which is changing the size of the aperture, how much light can come into the lens. But there's also stops set through the exposure duration. Anytime I double the amount of light that the camera captures, or cut the amount of light in half, no matter how I do it, that's called a stop. So if I cut the light in half, I went down a stop. If I double the amount of light, I've increased this by 1 stop. So it's the doubling. The reason I say this is important is because to get the corona is tricky. It is so bright near the sun that if you take the shot that lets you get the farthest reaches of the corona, everything even halfway to the sun, will be completely blown out. You will have nothing but a messy blob. So what you want is a nice, clean, crisp sun, and you're going to take high dynamic range by taking 12 different exposures and blending them together in post-processing software to make that happen. So the first shot that you take is at 1/1000th of a second. The next one you'll take is at 1/500th, 1/250th, 1/125th, and then 1/60th, we don't go 62.5. 60th is close enough. Then
Sure.
1/30th, 1/15th, then 1/8th. We don't do 7.5, just 1/8, that's close enough. Then 1/4th, 1/2, 1 second, and then a full 2 seconds. And that's 12 different exposures. You will then blend those results together, and you will get a gorgeous solar corona shot that you can put together. You can take one more shot, a 13th shot, which is a full 4 seconds long. That is long enough that if it's clear enough, you get this effect called earth shine. So you know, you go out at night and you see the moonlight on a full moon, and you don't even need to turn a light on because you have so much light. Well, it turns out when the earth, if you're on the dark side of the moon, and Earth's light is shining back on you, you get the same effect. So if you take a long enough exposure, you will actually see the surface of the moon in the exposure. And those are essentially the set of shots that you want to see if you can capture.
Interesting, interesting. It's a great way, as you describe it, so that the images can be sequenced.
Yep.
Now, what about scripts?
Okay, so there is some, if you use the Eclipse Maestro or the Eclipse Orchestrator, you can build these scripts and it will do it for you automatically, and it ties to your GPS, so it knows exactly what time it is, where you are, and it knows the moment that all of these events will happen. The contacts I mentioned, it knows precisely when those will happen. And so the scripts say 9 seconds before C2, and the software knows what that means. Send the camera a command to set the exposure to these settings that I laid out and capture that shot. And it will orchestrate it all the way through the eclipse.
Okay, and can those be purchased, or do you have to put those together yourself?
They will give you samples, and then you just test them out. Before the eclipse, you can put the software in simulator mode, and you make sure that the camera really is triggering for those. And they will have, I've given you the recommended exposures, and they will also probably be in the sample scripts that come. And then you will tailor it to make sure it knows to use your camera instead of a generic camera, and you're good to go.
And that would be the scripts that we talked about previously.
Yes.
Okay.
Yep. And you want to fully test this.
Yes, test, and test again.
Yep.
So how many eclipses have you imaged?
So I've only imaged the one in 2017. That was my first time getting to image an eclipse. It did actually go perfectly. Everything went right. Again, I was enjoying the eclipse, and the computer was automating everything. I had done numerous test runs before the day of the eclipse. And that brings us to some tips that we should talk about. So we mentioned when you're going to go do an eclipse, and I said I want to try and talk you out of it, but you're going to do it anyway. So part one, about 15 minutes before a second contact, you want to swap out the battery and memory card. It is not good to run out of battery in the middle of the eclipse. So do that. About 5 minutes before totality, double check the focus and that the sun is in fact centered. About 1 minute before, do it again. And then at least 10 seconds before totality, but not more than 50 seconds before totality, take the filter, or we talked about these filters, take that off of your camera, and then when totality actually hits, you can take your goggles off. When totality ends, put your glasses back on, and within 50 seconds, but at least 10 seconds after, put the cap back on in front of the camera. Other than that, enjoy the show.
It sounds like a great experience if you're prone or encouraged to, or interested, I should say, in taking some images of the upcoming solar eclipse on April 8th. So I want to thank Tim for coming in and giving us this very valuable information. Please check out our club website. The address is down there at the bottom of your screen. And coming up again, as always, is Stephen with What's Up in the Night Sky.
Thanks, Don. What's up in the night sky for December 2023? Now, in December, we have the solstice, the winter solstice in the northern hemisphere, and the summer solstice in the southern hemisphere. And that happens on December 21st. December starts with the third quarter moon on the 5th. The new moon is on the 12th. The first quarter moon is on the 19th. And then the full moon is on the 26th. That's when NASA can't go back to the moon because, you know, it's full. Then we have Mars, Mercury, and Venus shown on the 31st of the month at sunrise. So Mars is closest to the sun, where it will be almost all month. It's really going to be tough. It goes from Scorpius to Sagittarius over the month, staying near the sun. It is slightly better at the end of the month, rising about an hour before sunrise. Mercury goes from Sagittarius to Ophiuchus over the month, staying also very close to the sun. As the month starts, it sets about an hour after the sun, but then it has inferior conjunction on the 22nd, and at the end of the month, it rises about an hour after the sun in the morning, so on the 31st then. Max eastern elongation, that's when Mercury is farthest from the sun as you see it, apparently as you see it. That is on the 4th, which is, so it's slightly farther from the sun at the start of the month than at the end of the month. Again, it's pretty close to the sun all month. And then Venus goes from Virgo to Libra and rises about 4 hours before sunrise to 3 hours before sunrise. So it's a bit better at the start of the month. Then we have Uranus, Jupiter, Neptune, and Saturn. Uranus and Jupiter are in Aries and set from 2 hours to 4 hours over the course of the month, before sunrise. 2 hours to 4 hours before sunrise. Neptune is in Pisces and sets 6 hours to 5 hours after sunset. Note that Neptune is on the border between Pisces to the left and Aquarius to the right. In 2009, when this show started, Neptune was in Capricornus. In late 2010, it moved to Aquarius and is just crossing into Pisces now. Neptune doesn't move that fast. Saturn is in Aquarius and sets 6 hours after sunset to 4 hours after sunset. Saturn is also heading through Aquarius towards Pisces, while Neptune takes 165 years to go around once. It only takes 29 years for Saturn. Saturn will catch up. And that's what's up in the night sky for December 2023. Now remember, we don't charge money for this show, but we may tax your brain.